Hey everyone, I hope you're doing well. Welcome to a lesson on dividing fractions. If you need to check out my fraction basics video or my multiplying fractions video, they'll both be helpful in helping you understand this video here. In this lesson, I'll go over the steps on how to divide fractions and what reciprocals are and how to use them. Then I'll go through some examples on how to divide fractions with proper and improper fractions. Next, I'll go over dividing mixed numbers and whole numbers. Then I'll go into showing you some division fraction models and how to represent them visually. And I'll end the video with some application word problems. Let's get into it. Let's go over some important bits of information before we start some examples. First, it's important to understand that when dividing fractions, we're going to convert all whole numbers and mixed numbers into improper fractions. If you see a whole number like 4, we're going to have to convert it into an improper fraction like 4 over 1. And if you see a mixed number like 2 and 2/3, you're going to have to remember to convert that into something like 8 over 3. Second, we're going to have to rewrite all division problems as a multiplication problem. As an easy way to remember this process, we're going to call it keep, change, and flip. The keep refers to keeping the first fraction the same. The change refers to the fact that we're going to change each division problem into a multiplication problem. And the flip means to reciprocate or flip the fraction after the operation. If you had a division problem like 4/5 divided by 6/7, you would rewrite it as 4/5 multiplied by 7/6. Here's the keep, here's the change, and here's the flip. Once you've rewritten the division problem as a multiplication problem, just multiply as you typically would. Here we're going to multiply the fractions, but we're going to look to cross-cancel if we can. Here we can see that 4 and 6 have a common factor of 2, and if we divide by that, we get 2 and 3. Now that the tops and bottoms are relatively prime, we can multiply 2 times 7 to get 14 in the numerator, and multiply 5 times 3 to get 15 in the denominator. While I know it's a little bit strange at first, the algorithm for dividing fractions really looks like multiplying fractions instead. Dividing two fractions is equivalent to multiplying the first fraction by the reciprocal of the second fraction. Consider if you were dividing 2 by 1/2. What is this question really asking us? Remember, division is asking us how many times the second number, 1/2, fits inside the first number, which is 2. Imagine you had 2 cupcakes, and you cut them into half-sized pieces. How many pieces would you have? If you were thinking 4, you're absolutely right. Good job. Let's see if the algorithm checks out though. Since 2 is a whole number, we can rewrite it as an improper fraction, 2 over 1. We're going to keep that one. We're going to change the division sign into a multiplication sign, and we're going to flip or find the reciprocal of 1/2, which is 2 over 1. Now that it's a multiplication problem, we could do 2 times 2, which is 4, and 1 times 1, which is 1. 4 over 1 is just 4. Seems to check out. Please keep in mind that I'll be using the word flip and reciprocate or reciprocal interchangeably. When I say flip, I'm really saying to write the reciprocal. The reciprocal of a number or expression is a number that multiplies by the original to equal 1. For example, the reciprocal for 1/6 is just going to be 6 wholes. We know that 1/6 and 6 are reciprocals because if you multiply 1/6 by 6 wholes, you get 1. Also, the reciprocal of 7 would be 1/7. The reason is if we take 7 or 7 wholes and multiply that by 1/7, we do get 1 whole. If you have a mixed number like 4 and 1/2, you can convert that into an improper fraction, which is 9/2. The reciprocal for 9/2 would simply be 2/9. This makes sense because if you take 4 and 1/2 and multiply that by 2/9, that also equals 1. That's how reciprocals work. Now that we've gone over a little bit of background, let's try some examples together. In example 1, we're going to practice dividing proper and improper fractions. In this first example, we have 4/5 divided by 6/10. Remember our algorithm or steps that we're going to follow to divide fractions. First, we're going to keep the 4/5, then we're going to change the division to multiplication, and last, we're going to flip or reciprocate 6/10 into 10/6. Throughout the rest of the video, I'm going to represent the keep with a K, I'll represent change with a C, and I'll represent the flip with an F. Don't go thinking this is Kentucky Fried Chicken like KFC, it's KCF. Now that we have a multiplication problem, we can either leave them as 2 separate fractions, or we can combine them using one fraction bar. Here I'm just going to do that and write 4 times 10 in the numerator, and write 5 times 6 in the denominator. Looking to see if we can cross-cancel, I notice right away that 5 and 10 have a common factor of 5. If we divide 10 by 5, we'll get 2, and if we divide 5 by 5, we get 1. Also, I see the 4 and 6 and notice they have a common factor of 2. Dividing 4 by 2, we're going to have 2, and dividing 6 by 2, we'll have 3. Now that the factors in the numerator and the factors in the denominator are relatively prime, we can just multiply. On the top, 2 times 2 is going to be 4, and on the bottom, 1 times 3 is going to be 3. While you can leave it as an improper fraction, you could also convert it to a mixed number and say it's 1 1/3. Either one of these represent our quotient. Let's try another. Here we have 12/16 divided by 10/24. Remember the steps that we're going to follow. We're going to keep the first fraction, we're going to change the division to a multiplication, and we're going to flip the second fraction upside down, or find the reciprocal. Rewritten as a multiplication problem, we're going to keep the 12/16, we're going to change division to multiplication, and we're going to flip the 10 over 24 to make it 24 over 10. That's the reciprocal. As one fraction, we're going to have 12 times 24 up top, and we're going to have 16 times 10 on bottom. The GCF for 10 and 12 is going to be 2, 12 divided by 2 is going to be 6, and 10 divided by 2 is going to be 5. The GCF for 16 and 24 is going to be 8, 16 divided by 8 is going to be 2, and 24 divided by 8 is going to be 3. We can actually cross-cancel or simplify just a little bit more. This 6 and 2 that are left are not relatively prime. We can divide them both by 2. 6 divided by 2 is going to be 3, and 2 divided by 2 is going to be 1. Now that our top factors and bottom factors are relatively prime, we can multiply the tops 3 times 3 to get 9, and we can multiply the bottoms 1 times 5 to get 5. Our final quotient here is 9/5, or 1 4/5. I'd like you to pause the video and try this one on your own. When you're ready, unpause to see if we got the same thing. In example 2, we're going to practice dividing mixed numbers and whole numbers. In this first one, we have 4 divided by 3 1/7. When dividing, we really only want improper fractions and proper fractions. Rewritten as improper fractions, 4 is going to be 4 over 1, and 3 1/7 is going to be 22/7. Notice how 4 is equivalent to 4 wholes, and 3 1/7 is equivalent to 22/7. Now that we have improper fractions, we're going to use our keep, change, and flip. First, we're going to keep 4 over 1 the same, then we're going to change division to multiplication, and we're going to flip the 22/7 to write 7/22. With one fraction bar, we can write 4 times 7 over 1 times 22. 4 and 22 have a GCF of 2, we're going to divide 4 by 2 to get 2, and we're going to divide 22 by 2 to get 11. On top, 2 times 7 is going to be 14, and on bottom, 1 times 11 is going to be 11. You can also rewrite this as 1 3/11. Let's try one more together before you try the next one on your own. Here we have 5 2/3 divided by 17. Let's start by rewriting 5 2/3 as an improper fraction. 5 times 3 is going to be 15, plus the 2 on top is going to be 17. 5 2/3 is equivalent to 17/3. For now, we're just going to keep the division sign the same, and let's rewrite 17 as 17 wholes. Next, we'll remind ourselves that we need to keep, change, and flip. Here we're going to get 17/3 times 1 over 17. While you could rewrite this as one fraction, I'm just going to keep them separate. How convenient, the 17 and the 17 go into each other one time each, and they cross-cancel to make 1 and 1. Now that everything is relatively prime, we have 1 times 1 on top to get 1, and 3 times 1 on bottom to get 3. 1/3 is our quotient here. Now I'd like you to pause the video and try this next one on your own. When you're ready, unpause the video to check your solution. Here in example 3, I'm going to show you how to represent these division problems with area models. For this first one, it's our goal to create some sort of visual representation or area model to show that 1/8 does fit into 3/4 6 whole times. Using our algorithm, we know that 3/4 is going to stay the same or keep, the division is multiplication, and we reciprocate the 1 over 8 to 8 over 1. Cross-canceling, we get a 1 and a 2 here. Finally, multiplying, we get 6 wholes, which is indeed equal to 6. Here, I drew a rectangle and I cut it into 4 pieces. I cut it into 4 pieces because our initial fraction is 3/4. To represent this 3/4, I'm going to shade in one of these boxes, which is 1/4, shade in another, which is 2/4, and shade in one last one to make 3/4. These 3 boxes represent 3/4 of the whole. Now let's consider the 1/8. Remember, division is just asking us how many times does the second number, or in this case 1/8, fits into the first number, which in this case is 3/4. Here I take the same size whole and I divided it into 8 equal parts, making eighths. This right here represents 1/8. Our goal here is to see how many times this 1/8 fits inside of the 3/4. Here we can see it fits in once, twice, 3 times, 4 times, 5 times, and 6 times. Hopefully this area model helps you see visually why 3/4 divided by 1/8 is actually 6. It's because 1/8 fits into 3/4 6 times. Let's look at one more and see why 4 divided by 1/3 does get us 12. First, let's just check the steps as we know them. 4 is 4 over 1. We're going to change division to multiplication, and we're going to reciprocate or flip 1/3 to make 3 over 1. Since we can't cross cancel at all, we're going to say 4 times 3 is 12, and 1 times 1 is 1. 12 wholes is indeed equal to 12. Here I've drawn 4 rectangles to represent 4 wholes. Since we're dividing it by 1/3, we're trying to see how many times 1/3 pieces fit inside of the 4 wholes. Hopefully it's clear to you that we can see that 1/3 fits into 4 wholes 12 times. There are 12 of these 1/3 size pieces inside of 4 wholes. In example 4, let's try an application word problem. Ruby has 6 pounds of Halloween candy and eats 3/4 of a pound every hour. On the other hand, Jack has 8 pounds of candy and eats 4/5 of a pound every hour. Whose candy lasted more hours, and by how many minutes is this? Let's start with Ruby here. It looks like Ruby is going to keep eating 3/4 of a pound of candy every hour. Since she's going to continue to repeat this, she's going to do this until she runs out of candy. Instead of repeatedly adding 3/4 to see how many times it fits inside of 6, let's just do 6 divided by 3/4 to find out what it is exactly. 6 divided by 3/4 will let us know how much time it's going to take her to run out of candy. Rewritten, we're going to write 6 as 6 over 1, and we're going to keep the 3 over 4 for just a second here. Next, I'm going to keep the 6 over 1, I'm going to change division to multiplication, and I'm going to flip the 3/4 to 4/3. I'm going to cross cancel the 3 and the 6 to make a 2 and a 1. I'm going to multiply our remaining numbers to get 8 over 1, or 8 wholes. At this rate, Ruby's candy is going to last her 8 hours. Now let's talk about Jack. Each hour, Jack eats 4/5 of a pound of candy, and he keeps on doing this every single hour. Instead of using repeated addition, let's just take the 8 pounds and divide by 4/5 to see how many hours will go by before he runs out. 8 divided by 4/5 is the same thing as 8 over 1 divided by 4 over 5. Doing a little bit of keep change flip, we're going to have 8 over 1 times 5 over 4. With some cross canceling, we have a 1 and a 2 here. And multiplying, we're going to get 10 over 1. Simplified, this is just going to be 10. It's going to take Jack 10 hours to finish his candy. To answer the question, we can say that Jack's candy definitely lasts a little bit longer. Specifically, it's going to last him longer by 2 hours. Since 1 hour is equivalent to 60 minutes, we know that this is actually going to be 120 minutes. Hopefully, he'll share some of his extra candy with Ruby. Example 5, we're going to try one more application word problem. Lila knows that the area of her bed is 28 3/20 square feet. The length of it is 6 1/4 feet long. Draw a picture or diagram and label it. Help Lila find the width of her bed in feet. Here's a rectangle to represent Lila's bed. These measurements are pretty close to those of an actual full-size bed. Let's label our diagram. We know the area is going to be 28 3/20 square feet. Also, we know that the length of the bed is going to be 6 1/4 feet. What we don't know is how wide the bed is. We're going to use the letter W to represent the width here. The formula for the area of a rectangle is area is equal to length times width. Since we know the area is 28 and 3/20, I'm going to substitute the area with that value. Remember, 6 1/4 feet is going to represent the length. I'm going to substitute the 6 1/4 in for the length here. And since we don't know the width yet, we're going to keep it as W. If we know that 6 1/4 times something is 28 and 3/20, then we can say that 28 and 3/20 divided by 6 1/4 is equal to the width. Finding the quotient here is going to help us find us the width of Lila's bed. Let's start by converting 28 and 3/20 into an improper fraction. First, we're going to multiply 28 by 20, and that's going to equal 560. Then we're going to add on the 3 on top to get 563. This whole thing is still going to be over 20. 28 and 3/20 is equivalent to 563/20. Next, we're going to divide by 6 1/4. 6 times 4 is going to be 24, plus 1, which is going to be 25. 6 1/4 is equivalent to 25 over 4. Here we're going to do a little bit of keep, change, and we'll get 563 over 20 multiplied by 4 over 25. With some cross-canceling here, we can see that 4 and 20 are both divisible by 4, and we will get 5 and 1. In the numerator, 563 times 1 is still 563, and in the denominator, 5 times 25 is going to be 125. Since this is a word problem, let's convert this into a mixed number. We have 563 divided by 125. 125 times 4 gets us 500. That's going to be as close as we can get. Subtracting it, we're going to get 63. From this long division, we can see the width of this bed is going to be 4 and 63 over 125 feet long. Just so you understand, this is about 4.5 feet. In example 6, we're going to try a couple extension problems. Feel free to follow along, and you can come to office hours to ask me any questions later. In this first one, we have a division problem. I'm going to first write 20x to the 4th power times y to the 5th power over 18y to the 4th power. I'm going to leave that one alone. I'm going to change division to multiplication. Then, I'm going to flip or reciprocate the second fraction to write 45x to the 7th power over 30x times y to the 2nd power. Now I'm going to rewrite this whole thing with one fraction bar, and I'm going to rearrange it so it's a little bit more organized. We have 20 times 45 times x to the 4th power times x to the 7th power times y to the 5th power. Underneath, we're going to have 18 times 30 times x times y to the 4th power times y to the 2nd power. I basically just organize this so our numbers or coefficients are in front and everything else in alphabetical order. We can clean up the numerator and denominator a little bit by combining the x to the 4th power times x to the 7th power to get x to the 11th power. We can clean up the denominator by combining the y to the 4th power and y to the 2nd power to get y to the 6th power. Looking to cross cancel, 30 and 45 are both divisible by 15, and we'll get 3 over 2. 18 and 20 are both divisible by 2, and we get 10 over 9. 10 and 2 can be cross canceled to make 5 and 1. 3 and 9 can be cross canceled to make 1 and 3. The GCF for x to the 11th power and x is just x, so the x cancels out on bottom, and we have 10 x's left on top. The GCF for our y to the 5th and y to the 6th is going to be y to the 5th. All 5 y's are going to get canceled out on top, and 5 out of the 6 y's are going to cancel out on bottom. Multiplying everything we have left on top, we have 5 times 1 times x to the 10th power, which is just 5x to the 10th power. In the denominator, we have 3 times 1 times y, so we're just going to have 3y. This is the most simplified quotient of our variable expression. In this next one, notice that we have a subtraction and an addition sign. Instead, we're going to factor out the GCF of the difference in the numerator and factor out the GCF of the sum in the denominator. If their GCFs have common factors, we can simplify those. we can rewrite the numerator as 14a to the second power b times the quantity of 3ab minus 2. The denominator can be written as 14ab, which is the GCF, times a quantity of 4 plus 7a squared. Let's rewrite our fraction now. We have 14a to the second powered b times a quantity of 3ab minus 2 all over 14ab multiplied by the sum of 4 and 7a squared. While we can't cross-cancel sums and differences, we can cross-cancel products. Here we can see that 14 and 14 can cross-cancel to make 1 and 1, a squared and a can cross-cancel to just make a and 1, and the b's can cross-cancel to make 1 and 1. 1 times a times 1 is going to be a on top, times the quantity 3ab minus 2, and 1 times 1 times 1 on bottom is just going to be 1, so we're just going to be left with 4 plus 7a squared on the denominator. This would be the most simplified version of this expression. That concludes this lesson on dividing fractions. Feel free to use the timestamps to review any concepts that you need to. Keep up the good work, and I'll see you in the next one.